It's time for some more NileRed. Specifically turning children's glue into drinkable alcohol. I think we might be getting into making a nuclear reactor out of sand and duct tape territory. For those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
Done many projects where I turned completely inedible things into food, like that time I turned plastic gloves into grape soda and hot sauce, as well as that other time when I turned cotton balls into cotton candy. What I've been really wanting to do for a while, though, is to try turning children's glue into drinkable alcohol, and at least in theory, this should be possible.
So, industrial hazards aside, this sounds like it's going to be wildly inefficient.
This is because the main ingredient in most children's glue is a plastic called polyvinyl acetate, or PVA for short, and in its chemical structure, it contains all of these little groups here in blue, which are known as acetate groups. On their own, they aren't too special, but what I think is really interesting is that it should be possible to pull them off the PVA and to turn them into something known as acetic acid, which is essentially pure vinegar. Then after that, with just a bit more chemistry, I should be able to convert this acetic acid into some pure ethanol, which hopefully would be safe to drink.
So are we talking something close to Everclear? I don't know. Normally when I think of ethanol, I think of it in the industrial sense, like when it's used at a power plant, but I just don't know about this. I mean, he said hopefully safe to drink, so I guess we'll see. And I'm used to ethanol as being a type of hazardous industrial waste, though that's also because it has the potential to contain trace amounts of other chemical waste products in there. But let's see what he means by that.
I just thought that this whole idea sounded pretty fun to do, and I was also really curious to know what children's glue alcohol would taste like.
Of course.
So, despite the fact that...
So, instead of sniffing glue, you essentially want to eat the stuff. All right.
Wasn't exactly sure how to do it, and that I very possibly might end up just completely failing, I decided to just go for it.
Of course.
So, I just went ahead and got started, and the first thing that I was going to need was, of course, some children's glue, and I ended up going with Elmer's, which seemed to be the most common one.
He just has a drawer dedicated to having a massive container of Elmer's school glue. Not the type that you normally see kids using with the little safety caps on it, but all right.
I also decided to go with a full gallon, which is about 3.78 liters, and this may seem like a lot,
but it probably involves some horrifically inefficient chemical process, so you might go through the whole gallon to make a few drops of alcohol. Let's see if I'm right.
I had absolutely no idea how much PVA was actually in here, or how efficient the process would be.
Yeah.
But with that being said, now that I had the glue, it was time to try turning it all into alcohol, where the first step was to get a large dish, and to start dumping it in.
Sure.
This was because before doing any chemistry, I was gonna have to get rid of all the water that was in the glue, which was at least around 50% of its volume.
Sure.
I also figured that this was gonna be really simple, and that I basically just had to leave it out to dry, and I assumed that this was gonna go relatively quickly.
Nice.
However, that was not at all the case, and it turned out that drying glue like this was excruciatingly slow, mostly because the surface of it just quickly formed a really thick layer.
Yeah, I was going to say the vast majority of it isn't even exposed to the environment where it could dry effectively,
which prevented the water below it from evaporating. To fix this, though, I figured that I just had to keep peeling away the thicker layer and revealing the fresh, wet glue below it.
Sheets of glue.
I also set up a fan off-screen in an attempt to make this all go a bit faster, and at first, it seemed like it was gonna work. However, long story short, it only kind of worked, where it did definitely make it go faster, except even after 14 days of flipping it over and over, it still wasn't fully dry.
Wow, I heard of sitting for days on end to watch paint dry, but this is taking that to a new level.
It was only after wasting this
I don't know. I'm beginning to wonder if this sort of process is a bit like saying, can we convert depleted uranium into usable energy? And the answer is yes, you could. But you're going to spend so much energy adding in so many unnecessary steps that it's just not going to be worth it. You're essentially better off using it for something else.
time, though, that I finally accepted that this was an absolutely horrible method that would probably take at least a few more months. And it was pretty clear that I was going to have to try something else. So I decided to basically just do anything that I felt would speed it up, where the first thing that I thought of was to chop it up like a large cheesy lasagna.
You could use multiple trays at once. I mean, that'll give you more surface area that's exposed to the air so it can dry faster.
Which I thought would really help the moisture escape. I then tossed the whole thing into a food dehydrator to heat it up, and after a full week, it was looking significantly better. However, after manually tearing off some of the glue and peeling away the rest with my multi-tool, it was obvious that it still wasn't fully dry, and I'll be honest, after waiting almost a month already,
yellow glue,
I was really tempted to just consider this dry enough. As one last-ditch effort, though, I decided to try putting all of it into my new vacuum oven that I just happened to get earlier that week.
Yeah, vacuum pumps are used to remove non-condensable gases in the condenser of a nuclear power plant to overall increase your efficiency. So I guess this is all about increasing efficiency here too, just with glue.
With it all loaded in, I then pulled a vacuum on it, which would make it way easier for the moisture to escape the glue, and I ramped the temperature up to 80°C. I also kept it there, and I didn't raise it any higher, because at least from what I read online, anything hotter could potentially cause the PVA to start degrading. But either way, as the glue sat there, it did slowly get drier and drier, and eventually, after several more days, it seemed like all of the water had finally been removed. So I took it out, and now, after what was way too much effort and work, what I was left with were some super dry blocks of what was probably nearly pure PVA.
So even less of a reason to eat your glue because there's no water to dilute it with anymore.
At this point, it was also probably as dry as it was ever gonna get, so I just went and got my multi-tool, and I fully chopped it into pieces.
Can't say I've ever used a multi-tool on glue. That's interesting.
This then left me with a bunch of rock-hard blocks of glue, which I was pretty happy with, and after weeks of kind of wasting my time, I was especially glad that this whole drying part was finally done. The only unfortunate thing was that the struggle wasn't quite over, because all of this PVA was actually useless to me as these large chunks. This is because to do any real chemistry with them, I was gonna have to be able to get them into a flask, which meant that they would have to be way smaller. This in turn meant that I was gonna have to break them into a bunch of tiny pieces, and at first I thought this would be relatively easy, and I figured that all I had to do was get a cheap food processor and to shred it like cheese.
I need an expensive food processor.
Another long story short, that was absolutely not the case.
It's gonna break the blade.
And I ended up completely dulling out the blades and kind of breaking the machine. Uh-oh. I then moved on to ruining the blades in my blender, which also totally failed to break the part. And when I completely gave up and started just smashing it with a hammer, the only thing that I was able to break was my table. No! My table!
Oh, man.
That's not good.
This guy's determined.
Clearly, this glue was a lot tougher than I expected, and at this point, I was starting to worry that I might have to spend hours and hours manually chopping apart the squares using the multi-tool, which sounded absolutely horrible and probably wouldn't even work very well.
Just thinking about the overall inefficiency of this process, even getting the glue to be chopped up into a position where you could attempt to ferment, and acetic acid and its derivatives aren't exactly fermentable sugars, but I guess they're a bit closer, but anyway. This is equivalent to, I guess, trying to polish your depleted uranium, or cut and polish your depleted uranium before you even attempt to align it in a way that you would start up a reactor. It's still depleted.
After a bit of thinking, though, and searching online, I ended up finding what I felt was the perfect solution, and after a few days of waiting, I became the proud owner, the cheapest wood chipper that I could find on Amazon. Then when I felt ready, I went and got all of the glue and turned on the chipper, and I was somewhat concerned that the glue would still manage to destroy it. However, it was apparently totally fine, and it had no problem ripping it apart.
Glue chips.
And this was definitely way better than having to do all of this manually.
That's an interesting solution.
It was also kind of satisfying to see each piece getting sucked in, and...
By the way, if you try to put, like, uranium or even depleted, anything like that, you're absolutely breaking your wood chipper, but... Okay, I guess this is one thing this thing has over the analogy.
Obliterated by the blades, and over the next few minutes, I had a lot of fun dropping in the rest of the glue. The only problem was that when I was eventually done, it was very clear that the pieces were still way too big, and to get them smaller, I was going to have to pass them through again.
Ensuring secure deletion of your glue.
This part was unfortunately not quite as fun or fast, but it did work, and I decided to just keep putting everything through the wood chipper over and over. This then caused the pieces to gradually get smaller and smaller until eventually
make it into bath
I was
salt.
Reaching the limit of what the chipper was able to do. So I decided to stop here, and what I had now was a beaker full of small chunks of PVA, and what was nice was that they were all pretty much exactly the size that I wanted them to be.
Okay. Cool.
It was also very nice that this had only taken about 20 minutes instead of hours and hours of tediously chopping everything myself, and I'm very happy that I invested in the wood chipper. Moving on, though, with all
of... Who's going to get to use the wood chipper in future projects?
Now ready, I could finally start doing the chemistry to turn this into some hopefully tasty alcohol, where the first step was to turn it into pure acetic acid.
Okay.
From a bit of research, it also seemed like there was probably a few different ways to do this, but from what I could tell, the best and easiest way was to basically just heat it up. So that was what I decided to do, and to get started, I just quickly transferred all of this glue into the biggest round bottom flask that I had.
Nice.
I then dropped it into a big heating mantle that I'd bought just for this, and I clamped it in place, and I continued putting together the rest of the setup by first adding a three-way adapter with a thermometer in it, followed by a condenser column. With all of this in place...
It seems like NileRed has slowly accumulated a bunch of larger equipment and more sophisticated stuff since I started watching this channel. It's quite the operation he has.
And able to quickly finish putting it all together, and only a few minutes later, this was what I had, where the flask here was where I was hoping to collect the acetic acid, and the tube here was connected to my vacuum pump. This was very important because this all had to be done under vacuum and without any oxygen present, otherwise the glue would probably just burn or become a crusty, charred mess. With all that being said, though, I was just about ready to get started, and the only other thing that I still had to do was wedge a thermocouple between the flask and the heating mantle. This would allow me to monitor the temperature, and it wouldn't be super accurate, but it would still give me a decent reading of how hot the flask was.
Thermocouples are also good for fast response, or you can have them set up a certain way. In nuclear power plants, we often use thermocouples to measure the temperature of the of the water exiting the core. Note that you can't stick these things toward measuring the actual fuel. First off, the fuel is encased in cladding, and it is kept further away by the reactor coolant system. And a lot of thermocouples max out at 2300 Fahrenheit. Fuel centerline temperatures at full power will actually get hotter than that. Perfectly safe, just part of the chain reaction, heat from fission, and the uranium pellets can withstand that, the cladding can withstand that. Note that that's the center line. It rapidly drops off as you get away from the center of the individual pistachio-sized fuel pellets. But what you're actually measuring, one of the closest temperatures you actually measure is the core exit thermocouples, which is going to be the hottest part of the core because that's water that has just been heated by the nuclear fuel and will be pumped through the reactor coolant system to hit the steam generators and transfer the heat to the turbine to the generator to produce electricity. Number I was used to at the plant that I worked at, core exit thermocouple temperatures were about 620 degrees Fahrenheit for a reactor that's operating at 100% power. So pretty hot stuff considering you're measuring the fuel indirectly.
Now, with all of this in place, it was finally time to start cooking some glue. And to get things going, I started by flipping on my vacuum pump. I then turned on the heating mantle as well, and I raised the temperature dial slightly because the goal now was to heat things relatively slowly. This meant that at first, not much was going to happen, and, well, over the next 10 minutes,
controlled operations.
I really didn't notice much of a difference. When it eventually got to around 70 C, though, I started seeing some fogging down here, and not too long after, I saw the first drop of liquid fall into the other flask.
There you go.
However, when I looked over at the thermometer, which was showing me the boiling point of the stuff that was coming over, I saw that it was only around 20 C, meaning that this was probably just residual water that was getting cooked out of the glue.
Yeah. And boiling point goes down significantly depending on how much vacuum he's got drawn on the system. I know for a condenser in a nuclear plant was typically about 28 inches of mercury vacuum. Keep in mind a perfect vacuum is just under 30 inches of vacuum. Boiling point of water drops to on the order of 25, 30 degrees Celsius.
It then continued just like this for the next 20 minutes or so, where I got more or less continual drips, and the temperature of the glue flask slowly increased. This in turn made the drip rate increase as well, and when the glue eventually got to around 160 C, the stuff coming over started turning yellow, which I thought was a very good sign.
Something other than water.
This was because it likely meant that the glue was starting to degrade, and even though what I was collecting was probably still mostly water,
oh, definitely,
things were at least moving in the right direction. But either way, all I could do now was just keep waiting and hoping that the glue would really start breaking down, and, well, eventually, several minutes later, that was exactly what seemed to be happening. This was because at this point, it had not only become significantly more yellow, it was also starting to let off some smoke, which was then traveling through the rest of the setup and filling up the other flask. I actually didn't know exactly what this was, but according to a paper that I found, most of it was supposed to be the acetic acid that I wanted, which was forming as the acetate groups on the polyvinyl acetate slowly got torn off.
Nice.
The rest of this vapor, though, was supposed to be a bunch of other crap like acetone and carcinogenic benzene, which was forming as the PVA plastic in general was breaking down.
Well, it's under a vacuum in a controlled environment, so... Yeah, I was about to say something about how's he going to handle all the industrial waste that's produced from this sort of process. Because, yeah, there's a few things, some polymers that probably don't boil off completely.
This, in turn, meant that, in the end, I was probably going to end up with a horrible concoction of nasty chemicals, which wasn't exactly ideal, except that was something that I could worry about later on. But either...
As a nuclear engineer, hearing that, oh yeah, make some hazardous stuff that we'll worry about later on. Well, That's not unlike some strategies with nuclear waste. You put some of them in a secure location and you just have it decay on site, such as a reactor coolant system filter resins. They'll produce some radioisotopes that are in kind of intermediate level waste that just sit there on site until they decay away in a few days or weeks.
Getting back to the reaction, I quickly put together a little ice bath to try and help and condense the vapor, and when I looked back at the main flask, I noticed that the glue was significantly darker. From there, it then only continued to get darker and darker, and eventually, by the time the flask was at 200°C, it had developed a nice red color, and there was some nasty black liquid that had collected on the side of the flask. At the same time, the liquid that was coming over had also gotten a lot darker, and just by the color, I could tell that it was filled with a bunch of horrible and potentially carcinogenic chemicals.
Yep.
However, despite this, I was still very happy with how it was all going, because at least in theory, this was all still mostly acetic acid, and at this point, I had collected a pretty decent amount. From what I could tell, the rest of the distillation was also relatively straightforward, and I basically just had to keep heating it until the acetic acid stopped coming over. I, of course, had absolutely no idea when this would actually happen, but after about an hour, the temperature on the thermometer started rising much faster, which told me that I was starting to collect something else.
I think we're getting to a completely new fraction here.
Most of this was still probably acetic acid, though, so I decided to keep collecting it until it got to around...
Another reason why I'm glad he's using fume hoods. So this is, in the grand scheme of things, he says stuff like, we'll deal with that later, but it at least is set up in a safe way.
120°C, which was over triple the boiling point of pure acetic acid under the current vacuum pressure.
Okay.
At this point, there was probably almost no acetic acid coming over, and the rate had also slowed down like crazy, but I still wanted to keep going, just to be absolutely sure that I collected everything. This didn't end up going on for very long, though, because only a few minutes later, the temperature of the flask quickly spiked from the 230°C that it was at, all the way up to 380°C, which I really didn't like.
You reach a certain point where things can start to accelerate, usually when you get past the saturation point of certain substances. Kind of like there's various stages of boiling within a nuclear power plant, even a pressurized water reactor that doesn't have boiling in the name. Like nucleate boiling, you'll get some little bubbles show up in the pressurized water reactor. That's fine, and that's normal. The bad situation, which is if the fuel overheats too much or a sudden pressure drop, more often than not, the sudden pressure drop, you get into what is known as departure from nucleate boiling, where it starts to turn into film boiling, bulk boiling, and that's when the water starts to boil away, and eventually the core can become uncovered, and you can have fuel melting, fuel damage, if the issue isn't corrected. Fortunately, there's lots of safety systems, including automatic emergency shutdown if you do lose reactor coolant system pressure, so you turn the reactor off so that doesn't happen.
I don't like that. It just went up 150 degrees
in
like 30 seconds.
Oh, so, wow, that's fast. Okay.
I think it's done. I think there's like nothing left in the flask.
I was thinking a few minutes.
I'm done.
So I just went ahead and ended it here, and I turned off the heating.
There you go.
I then went over to the other flask, and I got rid of the dish of cold water, and what I immediately noticed was that it had actually separated into two distinct layers. This told me that there was for sure a whole bunch of nasty crap in there, and I was pretty certain that the black layer on top was mostly the carcinogenic benzene. Moving on, though, I then popped off the flask, and the moment that I took it out of the fume hood, I was hit by the smell of it,
that stuff's
which
nasty.
can only be described as a mixture of burnt plastic and gasoline, and it pretty much gave me an instant headache.
It's how the human body detects chemical hazards.
In my mind, this really reinforced the obvious fact that there was a whole bunch of nasty junk in there because pure acetic acid should have smelled
Just
much
vinegar.
more like really strong vinegar, and I was definitely going to have to clean it up. So that was exactly what I started doing, where the first step was to pour it all into the biggest separatory funnel that I owned.
And keep in mind, this is all to set up the thing that I guess replaces the sugar in a normal fermentation process.
To let it sit there for a bit, for it to separate back into two
Assuming
layers.
we're doing that, I don't know.
This
if
then
is.
happened extremely slowly, and even several minutes later, it was really hard to see any difference, but I felt that it was good enough, and I started draining everything into a large beaker. At the same time, I also looked very closely at the separatory funnel to track where that upper layer of nasty black crap was, and when it eventually got to the bottom of the funnel, I closed the valve. I then quickly got rid of all of this mystery oily junk, and now, when I looked over at the stuff in the beaker, I felt that it was already looking a bit cleaner, which was good. It was still super dirty though, and I would of course have to do a bit more work, except before doing that, I wanted to do a quick test. More specifically, I wanted to do a pH test because up until now, I hadn't really done anything to confirm that there was actually any acetic acid in here, and I'd basically been going on pure hope. So with that being said, I just went ahead and tested it, and I was kind of worried that it would show that there wasn't actually any acid in here, except that thankfully wasn't the case, and the paper had instantly turned a reddish pink.
I was going to say, probably more
this
acidic
told
than
me
vinegar.
that it was quite acidic, and that there was probably a decent amount of acetic acid in there, which meant that I was no longer just going on hope, and I could now move on with the rest of the cleaning. Also just kind of made up a procedure.
Yeah, at a nuclear power plant, procedures, especially ones that involve the creation of hazardous material that affect reactivity, that generate nuclear waste. Yeah, they have to go through a pretty big review committee before them. You can expedite it if it's an emergency, but yeah, I love that. I just thought of a procedure
that I figured would work, and to
also,
get started,
I figured it would work. Love it.
I dropped in a stir bar. Then into this, I added 400 mils of distilled water, which caused it to immediately turn white, and this was because a bunch of oily stuff that couldn't mix with the water was separating out.
Yeah.
All of the acetic acid, though, should have easily dissolved into the water, and after letting it sit for a few minutes, I started adding some regular baking soda. This caused it to immediately fizz and bubble as it reacted with the acid in there, which theoretically should have only been acetic acid, and it was turning it into sodium acetate.
Okay.
As a side product, it was also producing a lot of water and
carbon
CO2
dioxide.
gas, and my goal here was to basically just keep adding it until it stopped reacting. This is because at that point, all of the acetic acid would be converted to sodium acetate, and I figured that this would go relatively quickly. However, this process turned out to be really slow because every time that I added it, the bubbling took a really long time to settle down, and it was only an hour and nearly 1 kilo of baking soda.
Well, it's got all foamy looking, so maybe we skipped ahead to some types of alcohol. Yeah, I don't think so.
When it suddenly stopped reacting. The moment that I saw this, though, I knew that I was finally able to move on from this surprisingly long and tedious step, and what I had to do next was turn on the hot plate. So that was what I did, and the goal now was to slowly heat it up and to boil off any volatile organic junk, like the benzene, and then to get rid of any water. The key here, though, was that all of the normally volatile acetic acid was now protected by being in its sodium form, and in theory, once all of this other stuff was gone, I should be left with just solid sodium acetate. So I just kept heating it, and it was really satisfying to see all of the vapors coming off, knowing that a lot of it was benzene and other miscellaneous nasty volatiles. This also went on for a pretty long time, where the temperature just slowly rose, and it was only about an hour and a half later, when all of the volatile crap was gone, and the temperature eventually got to 100 C. At
There you
this
go.
point, it was probably mostly just water coming off, with maybe some residual oil and other trash, and now I just had to wait for all of the water to disappear. The only tricky part was that I had no idea how long this would take, and I was also pretty afraid of accidentally burning all of the sodium acetate, which only got more and more likely as the water content decreased.
Again, this whole process is just reminding me, too, of when you reprocess your spent fuel, where you use intricate chemical procedures. The difference in this case is they're quite heavily vetted, are employed to extract your usable fissile material so they can go back in the reactor. And it's not that efficient, but that is also one concern about nuclear reprocessing, is that is it really worth it with an abundance of uranium? And I'd say ultimately, especially if more nuclear power plants are constructed and more nuclear fuel is used, we'll eventually reach that point. But I can definitely understand the arguments for not doing it from that perspective. There's the other perspective about it, that with concerns of proliferation, but it is extremely hard. I mean, take this process here times 1,000, and not only you're dealing with hazardous chemicals, you're also dealing with radiological hazards at work. Because spent fuel, not to be confused with new fuel, is highly radioactive, the highest level of radioactive waste because of the fission products. That's one common misconception out there, is the fission products are, a common misconception is that uranium is super radioactive and hazardous. Well, not compared to the fission products like strontium-90 and cesium-137. Case in point, you can touch fresh fuel that's never been used because it doesn't have any of that outside of water without any concerns of dose. It also helps that it's kept in zircaloy cladding. The proliferation concerns, it's going to be very hard for the bad guys to get a hold of this stuff. That basically takes nation-state levels of funding in order to have these big reprocessing, repurposing, recycling programs for nuclear fuel.
So, to make sure that didn't happen, I ended up just staring at it, and for another hour, it really didn't look like very much was happening until it suddenly started looking like it was getting a bit thicker. Then, over the next 30 seconds, it got thick enough that the stirring had completely stopped working, and not even a minute after that, the entire thing had completely solidified. When I saw this, I immediately turned off the hot plate to prevent it from burning, and I was honestly really impressed with how much sodium acetate there seemed to be. I mean, there was a pretty decent chance that I'd added way too much sodium bicarbonate, and that was a lot of what was here.
The baking soda.
But I was still pretty happy with it. At this point, though, it was getting pretty late, so I decided to just leave it overnight and to let it cool down. Then, when I came back to it in the morning, I was ready to continue with the cleanup, and the first thing that I did was add a bunch of acetone. This is because this would easily be able to dissolve most of the impurities that were still there, as well as residual water, except it shouldn't at all be able to dissolve the sodium acetate. So in theory, this should allow me to basically wash the sodium acetate, and over the next few minutes, I just mixed it around as best I could, and I occasionally added some more acetone. During this time, the acetone also slowly got darker and darker, which I was very happy to see, and this told me that it was definitely pulling out a bunch of crap.
It's nice when you can chemically separate stuff. Unfortunately, in some nuclear processes, like such as enriching uranium, you can't really do that because uranium-235 is chemically the same thing as uranium-238 because it's all uranium. Chemical processes don't really care about how many neutrons the nucleus has. So you have to use processes like centrifuges in order to mechanically separate, because the only difference is the mass. So large, massive warehouses full of many stages of centrifuges in order to separate out all of the material, all of the uranium-235 versus uranium-238. And it's a big, cascading, iterative processes of constantly refeeding your product and getting rid of the waste products, which are known as tails in that situation. But you can also recycle some of them to just get more and more of the product out of what you're feeding. It's complicated, expensive, and it takes a lot of real estate. But you get nuclear fuel, and you can produce safe, clean, reliable energy for a long period of time.
When I eventually felt that it was done, though, it had become a really dark red color, and all I had to do next was dump it into another beaker. I also did my best to not lose any of the sodium acetate, and when I brought it back, I felt that the powder was already looking a lot better.
Now it looks like sand.
However, it was still quite yellow, which I really didn't like, so I had to just keep washing it with acetone until I felt that it was super clean. After a few washings, I also started heating the acetone and bringing it to a boil just to strip off any crap, and each time I thought that it was really satisfying to dump off all of the dark liquid. I then did what felt like a million more washings, where eventually the hot acetone was only turning yellow and the powder was looking way better, and I felt that this was good enough. So I quickly got rid of the acetone, and I did my best to transfer everything to a large dish. I then just let it sit there for a day or so, with occasional stirring to get rid of any residual acetone, and when the smell of acetone was eventually completely gone, I put the entire dish in my vacuum oven. I did this just to really make sure that it was absolutely dry, and when I eventually felt that it was looking good, a few days later, I took it out, and what I had now was some nice and crunchy powder. More specifically, though, this was a bunch of completely dry sodium acetate, where pretty much all of that original nastiness had been removed, and so far, I was very happy with how things were going.
All right, so we've went from glue into white powdery stuff.
This was especially because now I was really close to being done, where the only thing that I still had to do was convert all of this sodium acetate back into some pure and water-free acetic acid. As far as I could tell, this was also relatively easy, and all I had to do was transfer my dry sodium acetate powder to a large flask. I then put together almost the same setup that I used for the glue, except this time, above the flask, I included a separatory funnel that I'd filled with an insane amount of concentrated sulfuric acid. If this ended up tipping over or something, it would have been an absolutely horrible disaster, especially if it splashed on me.
Yeah, so something like this, you would have some level of separation criteria, some level of peer checking, as well as physical barriers, so those sort of chemical spills don't happen to you. At least that's the way it would be done if this was done at a lab at a nuclear plant.
And I honestly felt pretty uneasy suspending over 3 pounds of this acid in the air.
Pounds of acid, okay.
But with that being said, when I felt that I was ready, I just unleashed the sulfuric acid, and it started bubbling the moment that it touched the sodium acetate. This told me that it was definitely reacting, where in theory, it should have been turning it all back into pure acetic acid and forming sodium sulfate as a side product. It was also generating a lot of heat, which was enough to boil off the acetic acid and to fill the flask with a bunch of white vapor. This white vapor was then traveling out of the flask and down the condenser column and filling the receiving flask. After that, it wasn't long before I saw my first drop coming over, and at least theoretically, this should have been some nice and pure acetic acid. Also, because I'd put so much effort into drying the sodium acetate, and because I was using sulfuric acid, which really liked to suck up moisture, all of this acetic acid should have been completely water-free. But with that being said, this process...
I mean, I wouldn't count on complete water-free. That assumes a 100% efficient process is at work here. There's going to be trace amounts.
This was pretty simple, and I basically just had to keep adding the acid. Then, when I was eventually done adding it, All I had to do was swap the funnel for a thermometer and turn on the heating, and go until I stopped collecting any acetic acid. However, I had no idea how long this was going to take, and just like many of the other reactions that I'd done so far, it ended up feeling like it was going on forever. At some point, I also noticed that the stuff I was collecting was slowly getting more and more yellow, meaning that some sort of impurity was somehow making it over, which was kind of concerning. But either way, after a couple hours, I basically stopped collecting anything, so I turned off the heating, and left in the flask was just a nasty mixture of sodium sulfate and carbonized junk, along with some extra sulfuric acid. This was also trash that I didn't need anymore, and the only thing that mattered was what was in the other flask, which, according to my plan, was supposed to be super pure and absolutely water-free acetic acid. Unfortunately, though, nothing ever goes to plan, and the fact that it was yellow told me that it for sure wasn't pure, and that I was going to have to do a bit more work. This wasn't ideal, and it kind of felt that at this point, this cleanup was never ending, but on the bright side, I felt that this would be pretty easy, and that I would just have to quickly distill it again, except long story short, it was not easy or quick. This was because it turned out that not only was it dirty, it actually wasn't even close to being water-free, and there was apparently an insane amount of water in it, which I think came from adding way too much sodium bicarbonate. So unfortunately, even after distilling it, it was still full of water, and it didn't seem like just doing the same distillation again was gonna work.
Going back to the previous example involving reprocessing or even just processing nuclear fuel, yeah, you end up with essentially using tails. So back to the uranium enrichment process. So the yellow cake uranium that you know and love is converted into uranium hexafluoride in order to enrich it. But kind of like with the distillation process, you have some bits and pieces left over, and these are what's known as tails, basically tails of depleted uranium. So we're talking like 0.2, 0.3% enriched uranium, not that much more than natural abundance, but not by a whole lot, not a usable quantity to be used in nuclear reactors. But there you run into the economics of, is it worth trying to re-enrichment? And the answer is maybe, depends what the price of uranium is. But either way, they're typically stored as a byproduct. And if uranium prices do go up, it may be worthwhile to enrich that portion rather than having to get new uranium.
I really needed it to be perfectly dry though, which meant that I was gonna have to somehow fix this problem. And thankfully, after spending a long time searching online, I ended up finding something on the Science Madness Chemistry Forum that seemed like it would work. So awesome. I decided to just go for it, and the first step was to take all of my acetic acid and to add a bunch of solvent called dichloromethane, or DCM for short.
I can't say I've ever seen a design change go through at a nuclear plant through something they saw in a forum or some Reddit post or anything like that. It'd kind of be terrifying if that was indeed the case.
Then on top of this, I added some magnesium sulfate drying agent, which would pull out a bunch of residual water, and after letting it stir for a while, I filtered it all directly into a large flask. By doing this, I was able to quickly get rid of all of the magnesium sulfate, and eventually I was left with a nice and clear solution, which should have already been a lot drier. With that being said, though, I then set it up for yet another distillation, except this time I included this really long piece of glass, which is something called a fractionating column. This is because it would allow me to do a fractional distillation, where I would get a much better separation of water and acetic acid, and I just went ahead and cranked up the heating. The idea here was to then first distill off all of the DCM, which would come over at around 40 C, but the important part was that it wouldn't distill off alone, and it was supposed to pull any remaining water along with it. This was also exactly what seemed to be happening, because all of the DCM that was coming over was looking cloudy, which told me that it was full of water.
If you turn this contraption, this sort of system is also kind of like how steam generators work. You have a bunch of little chevrons in there to remove the moisture. This is kind of when you get towards the top of the steam generator. So you basically have as high quality steam, and by high quality, I mean the vapor fraction of it being pretty close to 100%, but you never actually hit 100%. But the point is, you want high quality steam to enter your turbine, more efficient process, and you're less likely to damage your turbine over time by having water impingement on the turbine blades. The difference is your steam generator has many, many thousands of these.
What was then a very good sign was that as I kept collecting it, the drop slowly cleared up, meaning that there was less and less water. And when all of the DCM was eventually gone, the temperature started rising. I then waited for it to get to exactly 118 C, which was the boiling point of acetic acid, and when it eventually got there, I waited about 30 seconds before quickly swapping the flasks. At this point, everything that I was collecting should have been absolutely pure and completely dry acetic acid, and something that I noticed was that, unlike all of the other distillation, there wasn't any fogging or smoke. But either way, I then continued collecting everything that came over,
and the
sign. Moment that the temperature started dropping below 118 C, I ended the distillation. I then took everything that I got, and I carefully poured it all into a nice bottle, and what I had now should have been 100% pure acetic acid.
Or
the
relatively
only sad
close.
part was that the amount that I ended up with was only around 100 mils, which was less than half of what I started with before trying to dry it. However, this still should have been more than enough, and I was extremely happy that I was finally done this part, and that I had some theoretically pure acid. To actually know for sure that this was acetic acid, though, I was going to have to do some tests,
pH
and
test.
I decided to start with the easiest one, which was to just see if it smelled like super strong vinegar.
It's one way to test it.
Okay,
It's like, the human body has built-in detection mechanisms, just like our eyes are radiation detectors. The nose is a chemical detector. Some people's eyes and noses are more calibrated than others.
That's definitely acetic acid. So, at least from this little acid-smelling experience, whoa. I was almost certain that this was pure acetic acid.
Laugh at these, but there are chemical tests, like a clear and bright for emergency diesel generators, where a chemistry technician just takes a sample of diesel fuel oil. And this is the ultra pure stuff in the nuclear industry. It looks kind of like red wine. And he just holds it up and looks at it and says, all right, you're good. They do a whole bunch of other tests too, but not every test is hard or invasive.
But to fully prove it, I was, of course, going to have to do some real tests.
He's going to taste it, isn't he?
So, the first thing that I did on it was an FTIR, which I then followed up with an HNMR. And I was very happy to see that both of these together...
Oh, nice. Real testing. I kind of forgot he had these. But yeah, so FTIR, Fourier transform infrared spectroscopy. Basically, it measures how functional groups, such as like an OH for alcohols, absorb infrared light. So you can just tell what it is. This is a similar general process to how you can tell what a radioactive source is, but here we're looking at very different energies and very different wavelengths. And you're looking at vibrational frequencies here. It's good for looking at stuff like polymers and identifying byproducts. The HNMR, you sometimes see it written as a 1-HNMR, referring to hydrogen, is hydrogen nuclear magnetic resonance. It looks at how protons respond to magnetic fields. And you can see here it pointing out the 1 hydrogen in the OH for acetic acid and the 3 hydrogen for the H3C. And it basically looks at how the spin states of protons flip in a magnetic field in order to do this. They're great for non-invasive analysis, kind of like gamma ray spectroscopy is for nuclear materials.
Fully confirmed that this was for sure acetic acid, and that it was quite pure. What I was most happy about...
The way you could tell the purity is the relative absence. I mean, there were some teeny tiny other peaks there of other things. If it was less than pure, you'd see a whole bunch of spikes everywhere, indicating you have, for lack of better terms, a mess.
Though, was that I could finally move on to the next and final step, where I would get to turn all of this acetic acid into pure ethanol, and again, in theory, there were many ways to do this. The only tough part was that, at least initially, every method that I found seemed to have some sort of major downside. After hours of searching, though, I ended up finding this paper, which described a process that appeared relatively easy, and it was supposed to have close to a 100% yield. In my mind, this was also by far the most promising method, and it seemed like it was my only real option, and I decided to give it a try. So I just went ahead and jumped right into it, and the first thing that I did was go over to my solvent cabinet, and I pulled out my DMSO. I then started pouring about 200 mils of this solvent into a large
very
flask,
scary-looking bottle.
And when it was all loaded in, I turned on the stirring. After that, I lowered in a little tube that was attached to my argon tank, and I started shooting in argon to push out all the air. I don't think this was absolutely necessary, but at the same time, this reaction was gonna produce a lot of hydrogen gas, and I was kind of paranoid that it could mix with the air in the flask and potentially explode.
That's a good conservative thing, using something like argon or nitrogen, something non-reactive, in order to do a purge. Hydrogen gas is something is a hazard that's well identified in nuclear plants, even in our battery rooms, have fume hoods in them just to purge any buildup, to prevent you reaching a volatile concentration.
But with that being said, the flask was now full of argon, and what I had to do next was add the first main ingredient, which was a bunch of white powder. This was all something called sodium borohydride, which is a strong reducing agent, and very soon, this was the stuff that would be releasing the hydrogen.
It's interesting. I like the thematic of doing something like, hey, okay, we're going to take some children's glue and we're going to turn it into alcohol, but you're using a whole bunch of other separate ingredients. It's kind of like, at what point do you just say, all right, we're just going to go ahead and start with some sugar and do some fermenting from there? But
right now, though, it was still relatively tame, and when it was eventually all added, I let it stir for about 10 minutes, just to give it some time to dissolve. Then, when I eventually felt that it was looking good, I went and got the second main ingredient, which was 9.6 grams of my beautiful acetic acid, and I started to slowly add it. This almost immediately caused there to be a bunch of bubbling, along with a pretty clear fizzing sound, and this was because the acetic acid was reacting with the sodium borohydride and releasing some of that hydrogen gas that I mentioned earlier. More importantly, though, it was supposed to be forming an intermediate known as sodium triacetoxy borohydride, which right now might not look like anything useful, but it'll be very important in a bit. Also, I should mention that the 9.6 grams that I was using here was only around 10% of the acetic acid that I had, and this is because at this point, I still had absolutely no idea if this reaction actually worked, and I was too scared to risk more than this. But anyway, once I'd added everything, I again had to let it stir for several minutes to make sure that it all fully reacted. While this was happening, though, I had to prepare the next major ingredient, and to do this, I started by adding an addition funnel above the flask. With this in place, I then went and got another chemical called methane sulfonic acid, and I added 53.8 grams of this syrupy liquid into the funnel. On top of this, I also added another 200 mils of DMSO, which easily mixed with it, except in theory, I probably shouldn't have been adding a solvent to an acid. I mean, in this case, I knew it would be fine, but that can't always be assumed. And for example, if I had done this with sulfuric acid and water, it probably would have boiled and potentially sprayed out of the funnel. But either way, once it was all mixed, I sealed the top with a stopper, and now I was ready to make some ethanol. So I just went over to the valve on the addition funnel, and I very carefully opened it to dropwise add the methane sulfonic acid, and almost immediately, I could see that it was reacting. This was because there were a bunch of very small bubbles that quickly appeared, which was all hydrogen gas, that was forming as the acid attacked the sodium borohydride. As far as I know, though, this was mostly just a side reaction, and what I actually wanted the acid to do was catalyze a reaction between the sodium borohydride and the sodium triacetoxyborohydride that I made earlier. The paper itself, unfortunately, didn't give any details about this reaction.
How long it takes.
But what I think is likely is that the sodium borohydride was splitting apart the sodium triacetoxyborohydride and turning it into something called acetaldehyde. This was then probably getting attacked again by the sodium borohydride, which would be reducing it even further, and hopefully turning it into some amazing ethanol. Overall, I thought that this was all pretty exciting, except what did concern me was that the paper also didn't give any real details about the reaction process itself, and unfortunately, even though it was still very early on, it was looking like it was going to be a temperamental one. This is because after barely adding any acid, it was already warming up, and at this point, it was getting up to around 40 C. It was also looking like it was slowly getting foamier and foamier, which would only get worse as it heated up, and I was definitely going to have to cool it down. So I just quickly added a large dish under the flask, and I filled it with a bunch of water, and this very quickly brought the temperature down to around 15 degrees Celsius, which I was very happy to see. This is because the crisis seemed to be over, and even though it was still bubbling, it appeared to be much more controlled, and now I figured that I just had to add the rest of the acid. So that was exactly what I did, and what I thought was really interesting was that as I added it, the reaction seemed to go through a few different phases. For example, for some reason, despite the cooling, it all started getting frothier and frothier again, except right when I started getting concerned that it might eventually foam out of the flask, it all suddenly thinned out. This then made me think that I was basically in the clear and that I was past the worst of it, but then it suddenly started thickening way worse than before, and it actually ended up completely freezing. At the same time, it was also slowly puffing up, which was very concerning.
I wouldn't have saw that one.
Except it, again, just suddenly started thinning out, and it wasn't long before it completely liquefied. This constant back and forth, though, made it so that I absolutely didn't trust it anymore, and I became constantly worried that at some point it could just start foaming uncontrollably, except that thankfully never happened. This is because it actually ended up being super tame, and when I eventually added the last bit of acid, I was left with a nice and slightly gray solution. At this point, though, the reaction wasn't quite done yet, and I was gonna have to let it stir like this for a bit longer, so while I was waiting, I went and got a beaker, and I added about 180 mils of water. Then after that, I dumped in 20 grams of sodium hydroxide drain cleaner, and I turned on the stirring. And I waited for it to fully dissolve. When this eventually happened, I had a nice and clear solution, and at this point, it had been about 15 minutes, so I went back to my reaction, which now should have been done, and I started pouring all of this into it. This strongly basic solution was then quenching the reaction, and it was destroying any sodium borohydride or acid that remained. For whatever reason, it also caused the whole thing to clear up quite a bit, and I started noticing little drops of something oily appearing on the side of the flask. But moving on, what I had to do next was get all of the ethanol that I hopefully made out of this mixture of chemicals. According to the paper, this was also relatively easy, and apparently, all I had to do was some more distillations. So I just immediately got started with...
What is that expression? 90% of chemists quit when they have one more distillation to go, or something like that?
That by getting rid of the water dish, And then I quickly added a stopper, a fractional column, and another stopper, and I put together pretty much the same setup that I just did for the acetic acid. I then cranked up the heating, and it wasn't long before the first stuff started coming over at around 35°C, which I assumed was that oily junk that I saw before. More specifically though, I was pretty sure that this was all something called dimethyl sulfide, which was supposed to be a major side product in this reaction.
That's one of those things that gives the ocean its smell because of the natural sulfur cycle.
The only unfortunate part was that it was also supposed to smell absolutely horrible, but at such a low boiling point, I figured that it would be removed pretty easily. With that being said, I then just kept collecting it until the temperature suddenly started spiking, and when it eventually got to about 80°C, I swapped the flask for a fresh one. This was because at this point, if there were any ethanol in there, this was when it would start coming over. The only tricky part was that it wasn't going to be coming over as pure ethanol, and it would instead be a combination of ethanol and water. This in turn meant that to get all of the ethanol...
That's how you drink it. You water it down to enough that the ethanol's a minor amount.
I was also going to have to collect all of the water that was in there, which was around 200 mils, and over the next couple hours, the volume in the flask slowly rose. At the same time, the amount in the main flask slowly went down, and with less and less water, a bunch of solid stuff started forming, and this was all just junk from the reaction that was being left behind. Going back to the other flask, though, it did eventually get to the point that it was around 200 milliliters, and right when this happened, I turned off the heating. I then quickly popped off the flask, and what I had now was, at least in theory, around 5% ethanol, which I thought was pretty exciting. However, just by looking at it and seeing all of the little oil drops that were still somehow floating around, it was obvious that I was going to have to clean it a bit more. So I decided to do another distillation, except this time I would use a much more efficient fractional column, which would hopefully give me a better separation
Look at all those
of
little
ethanol and water.
globes.
I then just went ahead and cranked up the heating, and I basically did the same thing as before, where I rejected everything that came over below 80°C. The major difference this time, though, was that I wasn't going to be collecting all the water, and I was actually going to try to leave behind as much as possible by pulling off the flask the moment that the temperature got to 100°C. So that was exactly what I did, and then I very carefully transferred everything that I got to a little vial, and at this point,
teeny tiny,
I was pretty happy with how things were going.
Nice.
This was because, assuming that the reaction had worked, what I had now should have been relatively clean ethanol. To fully confirm this, though, I was going to have to run it through my NMR.
Okay, I was going to say spectroscopy or taste test. Which one would you do first? I mean, the nuclear answer is obvious, but...
So that was what I did. And well, it told me that it wasn't super pure, but it was for sure ethanol. To get its concentration, I then did another test by putting a few
You never
drops
specified how pure it should be.
of the ethanol onto something known as a refractometer, and when I looked into it, it told me that it was at least 80%, which was actually better than I expected. The only unfortunate part was that when I went to do the very necessary smell test, I was not very impressed.
Very necessary. Maybe your nose is desensitized. Probably has coffee grounds around as a nose palate cleanser, for lack of a better word. I don't actually know what it's called, but I know coffee grounds is helpful for that.
This is because instead of getting a nice and clean ethanol smell, it was almost unbearably sulfury with a horrible rotten cabbage stench. I also almost immediately knew that this was all coming from residual dimethyl sulfide, which was somehow able to make it through the distillations.
I mean, that stuff is potent in small concentrations. I mean, we're talking about teeny tiny bits and pieces of it in the ocean that give the ocean its smell.
And I was honestly getting a bit worried that this might end up being a problem. At the same time, though, I felt that it was probably fine and that it could be easily removed with some more
I love how he
distilling.
convinces
And
himself.
instead, I decided to focus on how well this reaction had worked. I mean, the yield wasn't even close to the 93% in the paper, and it was more like 48% because they didn't fully isolate it like I did. But overall, I still really liked the process, and I liked that it was relatively simple and easy. So I decided to just keep going with it and to use it to convert the rest of the acetic acid that still remained, which was about 89 milliliters. The only problem with this plan, though, was that if I were to just repeat exactly what I did, I would have had to do it 10 more times, which sounded absolutely horrible. This is especially because it would have taken at least 10 more days of work, and to avoid this, I ended up just scaling everything up by buying a brand new 5-liter
Get
flask.
bigger stuff.
I then did the exact same reaction
One way to achieve scale, but again, kind of going back to this process being wildly inefficient.
before, except with way more of everything, and the only real difference this
More
time
of everything.
was that cooling it was a bit more difficult. When the reaction was eventually
something colder than
done,
ice.
it also looked really interesting, and it was kind of mesmerizing to look at, and it was a bit sad when I had to quench it by dumping in the solution of sodium hydroxide. But either way, after this, I then did the distillation to get out all of the water, except this time, instead of immediately doing a second distillation, I poured it all into a different flask. This was because, even on this ridiculously large scale, I was only able to process half of the acetic acid, and before moving on, I was good.
At the rate, a lot of these processes use a good bit of distillation. I mean, he might as well just go ahead and buy a distillery at this point.
And I have to convert the other half that still remained. So, that was exactly what I did, and when I was eventually done the reaction and distillation, I took everything that I got and I combined it with the stuff from the first half. This way, I would be able to distill both of them at the same time, which was just a bit more efficient than doing them separately. And when I was done a couple hours later, I had what looked like a pretty decent amount of 80% ethanol. I then took everything that I got and I carefully poured it all into a fresh bottle, and in total, it ended up being just over 80 milliliters.
80 milliliters from a gallon of Elmer's glue.
I then brought back the roughly 6 mils that I got from the first run, which together with this was now nearly 90 mils, and this was way more than I ever expected to get, and I was feeling pretty happy about it. The only problem was that right now, it was all still nowhere near drinkable because it all smelled terrible, and it likely tasted like horribly rotten cabbage.
Oh, man.
As I mentioned earlier, though, I felt that this would be relatively easy to get rid of, and that I would just have to combine everything and do one final distillation. However, just like everything else in this project, that absolutely wasn't the case, and even though I included a bunch of copper, which was supposed to help remove sulfur compounds, the final result that I got was still far from good. That smells pretty bad. I mean, it was definitely better, but it was still nowhere near drinkable, and to get rid of this stubborn crap, it was looking like I was just going to have to keep distilling it over and over. So, that was exactly what I did, and what I did as well was filter it each time through a mixture.
Did he count how many distillations? I'm curious. We got to be into the hundreds.
Of activated charcoal and ion exchange resin, which was basically just a deconstructed Brita water filter, and I think it helped.
Basically the same sort of concepts used when cleaning up the water chemistry in a nuclear power plant. Both the primary side, the nuclear side, and the non-nuclear side that you see in any sort of power plant, known as the condensate polishing system. Though on the nuclear side, everything runs, the reactor coolant system obviously runs through the reactor, and you'll occasionally get some hot particles that become trapped in the filter that will need to be sent through the liquid waste processing system and need to be treated and set aside in waste holdup tanks so they can decay away. You shouldn't have to worry about any of that stuff.
Overall, though, not only did this whole process turn out to be really time-consuming and tedious, it was also not very efficient. This was because to make any significant improvement, I found that I had to sacrifice quite a bit.
Not to imply he doesn't know what's efficient and what isn't, but just that a lot of these processes, he knows how widely inefficient it is, but he just wants to do it because he can, which I gotta admire.
Of the initial stuff that came over at ADC, this in turn meant that I lost more and more with every distillation, whereby the fourth one, I barely had any left.
Yeah.
However, on the bright side,
2 milliliters.
Everything that I was collecting now was coming over in the very narrow range of 80 to 81C, which told me that it was quite pure.
Well, on the bright side, every time he distills it, you end up with less and less of the stuff, so it takes less and less time.
There was also a very good chance that I'd finally gotten rid of that horrible smell, and that all of this stuff here was actually drinkable, which I thought was pretty exciting. It was then only 5 minutes later, when I was getting really close to being done, except what I had collected at this point was honestly a really sad amount of liquid. I mean, compared to what I'd started with, this was basically nothing, and in hindsight, I really should have avoided any method involving sulfur. Yeah. On the bright side, though, at least from what I could tell, it was looking like I'd somewhat managed to salvage things, and at this point, it was done, so I swapped out the vial. Now, all that there was left to do was to see how it smelled, and I was honestly kind of nervous and worried that it would be terrible.
Calibrate your nostrils.
And that I would have to keep distilling it until I basically had nothing. That's perfect. Except that thankfully wasn't the case. I mean, there was still a very slight hint of something else, but other than that, it basically smelled like pure ethanol, and when I ran the NMR, it was clearly way better.
Yeah, well,
more specifically, that massive impurity that was here was now just an extremely small bump, and when I compared it to an NMR of some ethanol that I bought at the store, it basically looked the same.
That's pretty.
I then tested the concentration using the refractometer, which told me that it was about 68%, and it was surprising to see that it was somehow lower than before. With all that being said, though, I was now finally done, and after what was probably way too much effort, it was looking like I had successfully turned a gallon of children's glue into some drinkable alcohol.
A few milliliters of drinkable alcohol. Allegedly drinkable.
What a sad amount.
Yeah.
At this point, there was also, of course, only one thing left to do, which was to taste it. And to see if all of this effort was worth it.
To see how drinkable it is.
So, that was what I had to do next. Except, as a quick warning, I should be clear that tasting anything that I make is always at my own risk.
Yeah.
And even if it seems fine, based on the NMR and other tests, there could always be something toxic or horrible still in there.
Those tests aren't 100% accurate, and yeah, you could still have a reaction. They do have blind spots, so yeah, just want to echo what he said.
But with that warning aside, it was finally time to see how it was, and I was honestly feeling a bit nervous. I guess I just have to go ahead and try it.
A nice little beaker shot glass. Oh.
Okay, I'll just taste it.
Smooth.
That's not good. I mean,
no.
There's the obvious.
Well, would it be good anyway?
Fact that it's almost 70% ethanol.
Yeah.
So it just burns.
Yeah.
But it definitely has a characteristic flavor. And when I think a bit more about it,
it's a bit like saying it's not a bug, it's a feature.
Definitely some sort of like some sort of volatile hydrocarbon, like gasoline or something. Definitely has
You see, and that's the industrial ethanol I know, is as it's a byproduct, and yeah, it usually plays with industrial product.
It has a chemical flavor to it. I don't know how else to describe it.
Flavor of chemical.
Overall, though, is it horrible?
I wouldn't drink it.
No. I think it's totally drinkable if you have nothing else. I mean,
what is the nutritional value?
Some poison in it that kills you, but besides that risk, it's kind of fine. So, in the end, it unfortunately wasn't the amazing alcohol that I was hoping for, but at the same time, I think that it was probably as good as it could have been. I also think that
it says quadruple distilled. It looked like it had to be way more than quad distilled. Maybe if you distill it up to 100 times, it'll taste better.
Weird chemical...
What does it say? Not safe, toxic. Does it say 19 milliliters?
Gasoline flavor makes it really unique, and maybe I'm just lying to myself, but I kind of feel like it's growing on me. Overall, though, I'm really happy with how my glue alcohol turned out, and what I think is nice is that I'm now officially building a little alcohol collection, and I can place this next to my toilet paper moonshine that I made years ago.
That's advanced. I just still like the idea of some people just sniff glue and he converts it into something that you drink it with.
I've also already set it up for there to be a third spot here, which is reserved for what is probably going to be my final project in this series, where I try to turn air into alcohol. This is actually a project that I mentioned over a year ago, and I just wanted to take a second to say that this whole time I have...
Talk about inefficiencies and how much air you would need to use. Man, you need to draw a vacuum on an entire office building in order to get your supplies for that.
Been working on it, and I'm hoping to finish it very soon. I should also say that the same goes to all of the other huge projects that I've mentioned over the years, like making magnets from scratch, graphene aerogel, carbon nanotubes, liquid helium, and tungsten cubes. In fact, although I haven't been posting much, I've actually been working on over 20 projects at the same time and spending pretty much all of my waking hours on them. And at this point, my brain's getting close to being overloaded with information.
Yeah, it can do that when you have multiple projects consecutively, but this was a fascinating one. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.